Have you ever wondered how machine learning algorithms manage to learn from data and make predictions? The secret lies in a process called empirical risk minimization. Imagine you're navigating a maze. The goal is to reach the end while making as few wrong turns as possible. In machine learning terms, this is like a model trying to make accurate predictions with the least number of errors. This is where empirical risk minimization, or ERM for short, comes into play. ERM is a principle used by machine learning algorithms to learn from data. It's like a compass guiding the model through the labyrinth of information, helping it make decisions that minimize the risk of making mistakes. Its purpose is to find a function that will make the fewest errors when predicting outcomes based on the input data. But what exactly do we mean by risk? In the context of machine learning, risk is essentially the cost of making an incorrect prediction. It's like taking a wrong turn in the maze. The more wrong turns, the higher the risk. So a model aims to make decisions that lower this risk, improving its accuracy. Risk is a crucial concept in decision-making processes, not just in machine learning, but across various fields. Think about it. Whether you're choosing a route to take on a road trip, deciding on an investment, or even picking out what to wear on a date, you're always assessing the potential risk and making a decision to minimize it. So, in machine learning, ERM isn't just about making accurate predictions, it's about finding the most efficient path through the data, the one that minimizes the risk of errors. It's a principle that underpins the learning process of many machine learning models. It's the reason why your music streaming app knows just what song to recommend next, or why your online shopping platform suggests products that catch your interest. So the question remains, how does a machine minimize this risk? The answer lies in empirical risk minimization. Empirical risk minimization, or ERM, is a principle in machine learning that guides the learning process. But what does that mean, and how does it work? Let's break it down. Imagine you're trying to predict the weather. You have a set of data like temperature, humidity, wind speed, and so on. You also have a target you're trying to predict, like whether it will rain or not. Now, you could guess randomly, but your predictions probably wouldn't be very accurate. Instead, you want to find a method or hypothesis that uses your data to make the most accurate predictions possible. This is where ERM comes into play. The principle of empirical risk minimization aims to do just that. It's all about finding the best hypothesis that minimizes the risk or error in your predictions. In other words, ERM is about finding the hypothesis that best fits your data. How does it do this? Well, ERM uses something called a loss function. A loss function measures how far off your predictions are from the actual outcomes. For example, if you predict it will rain, but it turns out to be sunny, your loss function would record that as an error. Using this loss function, ERM goes through all possible hypotheses or ways of predicting the weather in our example, and finds the one that minimizes the loss. That is, it finds the hypothesis that gives the smallest error when compared to the actual outcomes. It's important to note that ERM doesn't guarantee the best solution in all scenarios. It works best when the data is representative of the situation you're trying to predict. If the data is skewed or incomplete, the predictions might not be accurate. But when used correctly, ERM can be a powerful tool in the world of machine learning. In essence, ERM is the guiding principle that helps a machine to learn from data and make accurate predictions. It's like a compass directing the machine learning process towards the most accurate outcomes possible. So how does empirical risk minimization work in practice? Well, let's take a closer look. First, we start by defining the loss function. This is the measure of how well the model's predictions match the actual outcomes. It's a bit like a yardstick that tells us how far off the function can be as simple or complex as needed, depending on the problem we're trying to solve. Once we've got our loss function, the next step is to set up a hypothesis space. This is a fancy term for all the possible predictions our model could make. It's like a universe of potential outcomes. But don't worry, we won't need to explore every single one. Now that we've got our loss function and hypothesis space, we're ready to dive into the heart of the ERM process. This is where we start to apply our data. The aim here is to find the hypothesis in our space that minimizes the loss function. To do this, we use our data to test out different hypotheses and see which one gives us the smallest loss. It's a bit like finding the sweet spot in a game of golf. You're trying different swings, and adjusting your technique until you find the one that gets the ball closest to the hole. And just like in golf, practice makes perfect. The more data we have, the better our chances of finding that perfect swing, or in our case, the hypothesis that minimizes our loss. But remember, ERM is not about finding the perfect model that predicts every outcome flawlessly. It's about finding the best model given our data and loss function. Sometimes this means accepting a bit of imperfection. It's about balancing the trade-off between fitting our data well and keeping our model simple enough to make meaningful predictions. By following these steps, ERM allows a machine to learn from data and make decisions based on this learning. It's a powerful tool in our machine learning arsenal, helping us turn raw data into actionable insights. The significance of empirical risk minimization in machine learning cannot be overstated. It's the compass guiding our machines through the vast, tumultuous sea of data, pointing them to the best possible outcomes. But how does it do this? Let's dive in. Let's think of machine learning as a journey. Our destination, the best possible model for a given dataset. But as with any journey, there are countless paths that we can take. Some of these paths may lead us directly to our destination, while others may lead us astray. This is where empirical risk minimization, or ERM, comes into play. ERM serves as our guide on this journey, helping to identify the best path to our destination. It does this by minimizing the risk of error in the learning process. It's like having a built-in GPS system that helps us avoid taking wrong turns, steering us away from models that may look good on paper but perform poorly in practice. But ERM isn't just a passive guide, it's an active participant in the learning process, constantly learning from the data and making adjustments to improve the model's performance. It's like a seasoned explorer, always learning from past experiences to navigate new terrains more effectively. And just like an explorer, ERM doesn't always get it right the first time. It's a trial and error process, with ERM testing out different models, learning from their performance, and then making adjustments to improve future outcomes. But despite the challenges, the benefits of ERM are clear. It helps us find the best model for a given dataset, enabling us to make accurate predictions and insights from our data. It's a powerful tool in the machine learning toolkit, helping us navigate the complex world of data with precision and accuracy. Without ERM, a machine would be like a ship without a compass, unable to navigate the vast sea of data. It's the guiding light in our journey towards effective machine learning, illuminating the path to the best possible outcomes. And with ERM at the helm, we can confidently sail towards a future driven by data and powered by machine learning. Let's take a moment to recap what we've learned about empirical risk minimization. It's quite the enigma, isn't it? But we've taken this complex concept and broken it down into digestible nuggets of knowledge. We started by defining empirical risk minimization, or ERM for short. It's a principle used in machine learning to minimize the difference between the predicted and actual outcomes. Essentially, it's about reducing the error rate of predictions made by a model. We then moved on to dissect the ERM process. It's a meticulous process that involves selecting a model, identifying a loss function, and finally optimizing that loss function. The goal, to find the hypothesis with the least amount of risk. It's like finding the best path through a maze, where the path is our model and the maze is the sea of data we're navigating. Next, we dove into the impact of ERM on machine learning. It's a cornerstone of machine learning, the engine that drives the creation of accurate predictive models. It's the secret sauce that allows machines to learn from data, to understand patterns and trends, and to make educated guesses about the future. But ERM isn't just about making predictions. It's also about understanding the limits and constraints of those predictions. It's about acknowledging that there's no perfect model, only models that are good enough for a particular task. And it's about constantly learning and adapting, tweaking and tuning to get the best possible results. So what's the big takeaway here? Empirical risk. Minimization is a powerful tool in our data science toolkit. It's the method by which we train machines to learn from data and make predictions. And while it might seem complex and confusing at first, with a little patience and perseverance, it's a concept that can be mastered. Understanding ERM is key to understanding how machines learn from data and make predictions. It's a powerful tool in the hands of data scientists and machine learning engineers, helping them to create models that can accurately predict the future based on past data.